So thanks for joining this last lecture on the topic. Okay, so we are now on the third lecture. So now what we want to do is to discuss the main parts of the security proof. Okay, after in the previous lecture we defined security, and then I want to tell you also about a different model that we call device-independent quantum key distribution. Okay. So we ended in this stage, okay? So we said that in order to prove secrecy, which is the main part, we want a quantum proof extractor to walk, and for this we need to show that the state shared between Alice and Eve in the end of the protocol, before applying the privacy amplification, has enough mean entropy. Okay, and this is what we're going to do now. Okay, so so we need to again, we need our state. We can write it like this. Okay, so we have here this convex combination, this mixed state convex combination over all possible strings that Alice can have, and Eve holds some quantum information which is correlated with these strings that Alice holds. Okay, so if we prove that we have this enough mean entropy, then the quantum proof extractor will do the work. Okay. So the security proof itself has these three main ingredients. So the quantum proof extractors, we already talked about it. Okay, and then there are two other parts. So I'll discuss these two things, somewhat informal, some of them are extremely complicated, and I will just present the main statements that we have. Okay, and there is something really nice here. So we have these three different parts. So the quantum proof extractor is more something that comes from computer science, and then we show that it works also in the presence of a quantum adversary. Now we have these other two steps. So one is something that I call reductions to IID, and this part it will be based on tools which tell us a lot of things about entropies. This will be more of an information. It comes from the field of information theory. And the third ingredient here is something that we call an uncertainty relation. This is where the kind of fundamental quantum physics enters the picture, also in showing how can we prove security. Okay, so we have this nice combination of all these three fields together in order to prove the security of quantum key distribution. Good. So we have the data here that we collect. Okay, after the sifting. And as we said, we need to lower bound this the amount of entropy here. And I'm changing now a little bit the notation. So here I now just use the bold letters to indicate that this is now a vector. Okay, so it's many bits. So let's say this A is 0, 1 to the n. Okay, well, n is the number of rounds or number of rounds where we chose the z basis. Okay, and the question is, how do we analyze Eve's action over these n rounds? Okay, so this protocol is there are many rounds, and she can do adaptive strategies. Okay, and she can do some global operations on everything that she has. It can be very, very complicated. Okay, and also, she can we would like to think, okay, maybe here we got this random bit, we got some entropy, but maybe in this round she did something completely different, and in this round we don't get entropy. So sometimes she manages to choose the right basis and to measure, and then she doesn't disturb the state. Sometimes she doesn't. So these rounds, really, there is no reason to believe that everything looks the same, that we can kind of create the same amount of entropy in each one of these rounds. Okay, so it makes it very complicated when we're trying to think how much entropy we collected globally over during the entire protocol. It's not clear how to do that. Okay, so kind of wishful thinking, if you try to understand what's going on, start from the most kind of basic restrictive scenario. So let's assume that Eve uses the same strategy in each round and independently of all other rounds. Okay, so let's assume that she has, for just a single round, she prepares this state, sigma, this tripartite state, sigma A, B, E. She gives A and B to Alice and Bob, and she keeps E for herself. Okay, and let's assume that she's just doing the same thing in each round here. Okay, so for each round she will distribute this state, and then Alice and Bob will make their measurements, and she will keep this marginal of E to herself. Okay. Then this initial state of the entire thing, okay, if I want to write a state of the entire, for the entire protocol before Alice and Bob made their measurements. So this I can denote it by rho ABE, which is a tensor product. It's an n tensor product of this state sigma. So state sigma is kind of a small state for just one round, and this rho is this tensor product for all of these rounds together. Okay, now if this is the case, then intuitively we can understand we only need to understand what's the kind of physics, what happens in one single round, okay, because she's doing exactly the same in all of the rounds. So if we understand the physics and the essence in one round and how much entropy we get in one round, then we can understand what's going on globally on the entire state. In this case, in this situation, we call it the IID case, okay, because the state is independently and identically distributed state. Okay, so that's just a name. Okay, and indeed, this intuition is true. It's not trivial, but there is a property of entropy of these IID states, of these tensor product states, which is called the quantum asymptotic repetition property. So this is again, you can see the references in the PDF file. So this is this statement here, which is maybe a bit hard to understand. So we have here many different entropies. In general, there are tons of different entropies. So far we talked about the mean entropy in this classical quantum case. Now I have here on the slide two different entropies. So this they all, before we don't even need to understand exactly what each of them means, but the important thing maybe to first of all understand is this: all of these entropies, they kind of describe some form of uncertainty or lack of knowledge. Okay, so they have different definitions, and they correspond maybe to different tasks, or they have a bit of a different meaning, but they all describe some form of uncertainty. Okay, of how much we don't know about A. Okay, or how random A is. Okay, so the entropy that we have here, this is called the smooth mean entropy, the smooth conditional mean entropy. I will not define it exactly, so it's closely related to the mean entropy. So it's basically like saying just take an optimization problem over all possible states which are epsilon close to this state rho here. But you can think of it as more or less the same as the mean entropy. The important point is this is actually the quantity that matters for us when we want to extract a key. So in the sense that this is good, it's a quantity which is relevant. It's good for extractors. So when I defined extractors in the previous lecture, I did all the definitions with the mean entropy, not with the smooth mean entropy, but you can define everything with the smooth mean entropy. And just add some epsilon in the error terms, and it's all good. Okay, and it's actually even better. Okay, so this is the quantity that we have here. It's the smooth mean entropy, and this is so far I said okay, I want to bound the mean entropy. So now I'm kind of just switching, saying I want to bound the smooth mean entropy. They're kind of closely related. I just want to work with this quantity. Okay, the second entropy that we have here is what we call the von Neumann entropy. Again, conditional von Neumann entropy. This is a quantum version of the Shannon entropy. If you've heard about the Shannon entropy from classical information theory, it's always larger than the mean entropy. As the name maybe suggests, the mean entropy is kind of the minimal. These are the formal definitions if you care about the formal definitions, but it's not relevant for us for the lecture. Okay. So what we have here is this statement, this relation between the entropies in the case of having a state which has this IID form. Okay, and the important thing to note is that we have, so if we have n rounds, we have n copies of this IID state, then what we see here is a lower bound on this smooth mean entropy. So this is what we are looking for. In the first order in n, this linear term in n, we have this von Neumann entropy, and this von Neumann entropy is now for a single state. Okay, so if this is these bold letters here, we have just this sigma, just what happens in just this single round. And then we have a second order term which scales like square root n. Okay, and here there is some constant dependence on parameters, but not on n. Okay, so this basically tells us that in our proof, if we want to get a lower bound on the smooth mean entropy and then say, okay, the extractor works, what we need to do now is we need to focus on this single round quantity, this von Neumann entropy, for sigma for just this state in a single round. Okay, so this is what we need to do in order to get a lower bound on this entire thing. So that's very good. So at least in this IID case, we know what to do. And of course, that was only a wishful thinking. So there is no, the adversary doesn't need to act this way. But there, there is a theorem, which is called the entropy accumulation theorem. And it tells us that under certain conditions about the physical process, that the protocol that describes what happens to our systems, this statement here about entropy still holds. Okay, so okay, I think the constant here is a bit different, but the important part is that we still have this second order term, which is square root n, the first order term, which is linear in n, and we still have this this von Neumann entropy here. Okay, so also in certain cases, for certain scenarios, and relevant for us, for our protocol, the entropy accumulation can be applied. We still have this statement here. Okay, now maybe it's interesting to just understand. So if we don't have this IID structure, if the state rho is not this many copies of sigma, so it's not that clear what, you know, when I write sigma here, what I exactly mean. So roughly speaking, this sigma is kind of a state that minimizes the entropy over all states that are compatible with what Alice and Bob are going to observe throughout the entire execution of the protocol. So if I look at the entire protocol in this, using this this figure here, so I'm starting with some initial state, and there is the part that belongs to Eve. And then the protocol, you can see it as applying a sequence of maps, a sequence of like you have the state, and then you perform some measurements. This is the first round. And then something happens, and you apply the second round of the protocol, and so on. And this is kind of a general structure of some sequential protocol, okay, or sequential process. And in the end, you get the final state, which is shared between Alice, Bob, and Eve. Okay, so this sigma here, or this function, the thing that we need to plug here is kind of like saying, you know, you're in the middle of the process here. You don't know what exactly happened already with Eve and with Alice and Bob in the previous rounds, but let's do some minimization and take the worst case von Neumann entropy as a thing that will kind of estimate what happens in a single round. Okay. And this, you know, the way I see it, I see this as kind of as a reduction to IID, not in a black box manner, in a sense, not it is, I can always say that this works. There are still various conditions that needs to hold, but if they hold, then basically what happens here is that, you know, if in the IID case, I had this situation where I had Alice and Bob device, if I look just in a single round, I had a state for Alice and Bob and Eve, I have their devices and Eve state, and I just do the same thing many times, then the asymptotic equipartition property told me that I can actually analyze just the entropy, the randomness which is produced in this single case. Okay, now the entropy accumulation tells me that also in some more general case, if there are some conditions that are fulfilled, then I can also do the same and kind of say, okay, let me just analyze what happens here. And if I manage to analyze this situation, then I plug it back into this relation between the smooth mean entropy and the von Neumann entropy of this single round, and I still get a lower bound on the smooth mean entropy. Okay, so this is what I mean by a reduction to IID. Instead of just, you know, considering all the complexity that I have here, I can just think of a single round as if I'm in the IID case. Okay. So now this is what I'm going to do. I'm going to just assume that I have this sigma here that Eve is choosing, and what I want to do is to bound this amount of entropy in this IID case, and I just forget about the more general thing. Okay, and then our goal now is to find a bound to understand just this von Neumann entropy for this state sigma. Are there any questions so far to this idea of reduction to IID?
We have one question here. So data, when you say data that Alice and Bob observe, does data mean classical information, or could it be also quantum?
Okay, so right now I mean classical information. So I mean, again, I will not get into details. We will see in a second what happens in the IID case. But I mean, for example, the estimation that they do for the errors. Okay, so when they check these the errors and they see how much errors they observe. Okay, so this kind of, we need to take into account when we do the minimization, we need to take into account all possible sigmas that can lead them to observing. So all the possible sigmas such that, for example, when they both measure in the X basis, they see this average amount of errors that they will see when they actually execute the protocol. Okay, so let's say the protocol is such that it says, okay, above 20% errors in the X basis, I abort. Okay, so I need now to do a minimization over all possible states, okay, such that there is a 20% chances of getting error when Alice and Bob measure in the X basis. Okay, so this is this classical information. This is the classical information. It should be kind of compatible with what we see during the entire execution of the protocol. The theorem itself, it's much more general. Okay, so you can, again, there are certain conditions, but you can play with it. You can put a lot of things, and some I think you can, yeah, it really depends on the protocol. I think there is like, you can formulate it with also putting some quantum information there, but it's very delicate. You need to see how you play with it. Okay, but right now what I mean is just this classical information. So for example, in this protocol, how many errors they observe.
Okay, I think that there are no more questions at the moment.
Okay, good. So now I'm going to stick to this. To stick to this IID setting. Okay, so I just have this sigma state. You can imagine that if is just giving the same state in each and every round now. And what we need to understand is we need to understand how much entropy can be produced from this particular state. How much of this, how much this von Neumann entropy can be produced from this single state. And once we have it, this kind of determines the first order term for the entire amount of smooth-mid entropy. Okay, so this was the reduction to IID. As I said, this is kind of information theory. There is a lot of these different entropies. Okay, now we move to the physics part, which is this what we call uncertainty relation. Okay, so we have a tripartite quantum state, sigma ABE, okay, that Alice and Bob share. Okay, and now Alice is measuring it either in the Z basis or the X basis. Okay, this is what the protocol says. And Henry talked about it yesterday, about the concept of an uncertainty relation, Heisenberg's uncertainty relation. What he said is basically, okay, we have some incompatible bases, and this means that we can't guess both outcomes with certainty. Okay, and the Z and the X bases are indeed they're incompatible. They're just rotated bases. Okay, so one way to quantify it is in this entropic way. So this is an entropic uncertainty relation. Okay, that we're basically, you can see this in this way. So again, this is the phenomenon. Now it's a phenomenon entropy, Shannon entropy. So now I have a new notation here. So the when I write A and then I have this Z or the X, and it means that I'm taking the A system, the quantum A system, and I'm measuring it in the Z basis or in the X basis. Okay, so Alice can choose one of them. And the point is that you can't have both, you can't guess both of them correctly at the same time. Okay, so if there is, for any state, if you can guess one with certainty, so this certainty will correspond to entropy here being 0, then the other one is completely random, okay, which this corresponds to this one being 1. Okay, so the fact that we have this sum of the entropies must be greater or equal to 1, this means that we have this uncertainty relation in the incompatible basis. We can't guess both outcomes. Okay, so now you can maybe start seeing how this is related to our protocol. So the Z basis, we're going to use it for the row key, the thing that we're going to construct the final key out of. And the X basis, we're going to use it for testing. Okay, so this is why it's important that we have both of these things. Okay, but it turns out, so this is kind of the most kind of basic entropic uncertainty relation. It turns out that we can also take into account the fact that Alice and Bob are entangled. So given access to Bob's system, one can actually do better. Once Bob is entangled with Alice, then Bob can help us guess better. Okay, so the uncertainty relation then, once we want to take Bob into account, okay, this B here is a quantum system. Okay, so Alice can measure in the Z, or she can measure in the X, and B here is the quantum system from the state sigma. A here in this entropy is also is the quantum state here. Okay, so you can get an uncertainty relation that has this form. Okay, and here, okay, so this is how well Bob can guess Alice's outcome if she measures in the Z basis. This is how well you can guess if she measures in the X basis. Okay, now instead of just having the one, we have this additional term here, which is the entropy of A given B, and these two things are quantum systems. And this is actually negative when Alice and Bob are entangled. Okay, so this is something that you don't see in the classical world, the negative entropies. So, okay, if you take the definition from before, or you can just believe me, for the maximally entangled state, for example, this thing is -1. Okay, so this is kind of full entanglement. Okay, so if Alice and Bob are entangled, let's say indeed they're maximally entangled, okay, this one becomes 0. So this is the relationship, this uncertainty relationship is trivial. Okay, so it's always greater than 0. And indeed, Bob, you know, if you ask Bob to guess what Alice will get in the X basis, or if you ask Bob to guess what Alice will get in the Z basis, he can just measure his side, his part of the state, because they're maximally entangled, and he can predict what she will get, right, in both of these things. So when we take into account this entanglement between Alice and Bob, then the uncertainty relation, this entropic uncertainty relation, becomes this statement here. Okay. Now, you can play with it a bit, okay? You need to use some entropic relations, some equations that I skip here. So you can play with it a bit, and then you get this this new equation here, okay? So this is just, again, some kind of transformation that you get from quantum information theory, nothing which is very fundamental for us for right now. So you can play with it, and you get this thing here. But here we have something which is very, very nice. So again, this is our protocol. Okay, so this is what we see here. So what we have here on this side, on the left-hand side, is Eve's uncertainty regarding the row key bit. Okay, so this is when Alice is measuring the Z basis. This is what will construct the row data, and Eve is E here is Eve's quantum system. So this is how much she knows about Alice's outcome. Okay, this is how much Eve knows from her quantum system about Alice's outcome. Okay, so this is, you can, you know, intuitively understand this is something which is the fundamental thing for our security. Okay, and this is indeed what we need in order to lower bound this total amount of smooth mean entropy with this asymptotic repetition property, or the entropy accumulation. Okay, so we said that to lower bound this thing, the entire amount of entropy that we get from all of these Z rounds, we need to know how much von Neumann entropy we can get from a single round. Okay, so this is this term that we have here. Okay, on the other side, we have here this error rate kind of thing. Okay, it's when when both Alice and Bob measure in the X basis. Okay, if everything is perfect and there are no errors, right? But when there are some errors, okay, this is the thing that they estimate when they execute the protocol. This is the thing that they're counting how many errors they have, and then they can get this quantity. So this kind of term, this entropy, can be estimated from the observed data during the execution of the protocol. Okay, so again, during the execution of the protocol in the X basis, Alice and Bob share the information of their outcomes. Then they see how many errors they have, and then they have this quantity. Okay, so this is something that we know that Alice and Bob know when they execute the protocol. Okay, so again, just an example from before. So the perfect correlation, if we have these EPR pairs, so there are no errors. So this thing here will be 0, okay, which means that here we get 1. Okay, so this bit, the maximum amount that this can take is 1. Which this means fool's entropy. It means fool's randomness. It means that Eve knows nothing about Alice's outcome in this perfect case of the EPR pair. Okay, so that's the very important thing now to understand from what I just said. Okay, so this is kind of maybe take-home message from this. So we have here these two parts. One is Eve's knowledge about the key. Okay, and the other thing is something that Alice and Bob can get from the observed data. Okay, so quantum physics, having like this uncertainty relation, quantum physics basically allows us to bound Eve's knowledge using Alice and Bob's observed data. Okay, so from looking at their own data, they can say, okay, Eve cannot know a lot. Okay, and this is kind of, I think this is really the essence of the way that we're using quantum physics and quantum key distribution. This is what allows us kind of to replace some computational assumptions or any other assumptions about the adversary. Like instead of coming already to begin with some assumption about what the adversary can or cannot do, can or cannot know, here we don't make any assumptions, but Alice and Bob during the protocol, they can check for the statistics and they can see, okay, you know, our statistics are sufficiently good. It means that Eve doesn't know a lot about the state. So from what they observe during the execution of the protocol, they know what Eve knows. Okay, so this, yeah.
But Alice and Bob just said, how can they estimate it if they only compare a small fraction of the positions?
Well, small fraction, but enough, right? So they don't like look at 2, right?
Okay.
So maybe in the maybe a way to think about it, like in this IID setting. So you can just you know, like a Chernoff bound kind of statement. So if you imagine that they all in all the rounds they have exactly the same thing, right? So you take some fraction of the rounds. Okay, so it's not 2, but it can be like it can be a linear fraction. It can also be less, actually. Okay, and then if you know that there is this IID behavior that in every step the same thing is happening, then by looking just at the subset, and if n is sufficiently large, then you know that you're picked right from the Chernoff bound. So you know that you got the right estimation up to some L. Okay. So it's sufficient to just take a fraction of the rounds, check the L's there, and then because of this, the assumption that they're using the same state in every round, and you know take n to be sufficiently large, then you know that you have the right estimation.
Okay, and one more question: the bound is tight.
This bound?
Yeah.
So I think this bound is tight. I presented here just for a very specific case where Alice and Bob measure in the X and Z basis. So I'll get to this later maybe. But I think for this particular case, I think this is tight. So again, if there are no errors, then basically we get one bit, which is the most that you can ask for. Okay. I think that for this particular case, yes. In general, I don't know, but yes.
Okay, thanks.
Okay. And in any case, there is again in the reference PDF, there is a reference to the paper that proves this, and you can check the details there. Okay. Okay, so that was the good point for the question. Okay. Okay, so what do we have here? We have the uncertainty relation, the physics. So we get this this bound here. Okay. Then this we plug it into this entropy accumulation to the reduction of IID case. Okay, so once we understood what happened in the single round, we plug it here, and we get a lower bound on the total amount of smooth mean entropy of how much we got in the entire thing. I'm switching notations here, so forgive me. Once we have a bound on the total amount of smooth mean entropy, then we can apply the extractor as we saw in the previous lecture. Okay, so we take this A, apply the extractor. So all of this can be AZ, okay? Doesn't really matter. So we apply the extractor, and then we get the promise of the extractor that we get something which is close to the ideal case, okay? This we are using now in order to prove that this trace distance here is small. So this gives us the secrecy. Okay, and from this we get a security that we talked about, the security definition that comes from the from the abstract cryptography, the composable security definition. So we get this gives us the secrecy. The correctness is, as I said, relatively easy because of the classical error correction, and completeness. Okay, we need to say that there is a device that that can be implemented. Okay, so this gives us the security proof. Okay, this ends this. Okay, so this maybe just explains like why I showed you everything that I showed you. I showed you in this direction, but now we see how it all fits together. Okay, good with questions, or before I move on?
Yeah, you can continue.
Okay, continue. Good. So you have kind of a fair understanding, or we didn't see how exactly we prove each of these things, but I hope you have like a fair understanding of how this thing looks like and the different challenges that we have in each point, okay, and what we're trying to do. So I want to move now to the last part, to what we call device-independent quantum key distribution. So it's a different model for quantum key distribution. So I want to motivate it to tell you about non-local games. These are kind of the essence, the physics essence that underlies the security of this QKD, this type of QKD protocols, and then the security. Okay, so in the Accurate 91 protocol, we had this scenario here. Okay, so we had Eve was choosing the state to distribute to Alice and Bob. Okay, and Alice and Bob measured the state either in the 0 or in the X basis, and the physics that was kind of the essence, the physics that we needed was this uncertainty, the entropic uncertainty relation that we just saw. Okay, but this particular uncertainty relation, it's this one, for example, it comes from the choice of the Z and the X basis. Okay, so if the measurements are not exact, then this is not one, it's something else. So again, you can look it up in the paper. But what if we don't even know the dimension? So what if this is not a qubit, it's something else? So for example, if there are some side channels in the actual implementations, then it might be that Alice and Bob are not getting qubits. You know, maybe they don't really measure something like in the qubit space, but something larger. So there are many different things that can happen. You know, you can start thinking of all different ways of attacking like an actual device. And then, of course, one way is probably also happens in classical cryptography when something is being hacked, and you can, okay, start, you know, changing this uncertainty relation, changing something else, or say, or here is a way to protect ourselves against this. So that's one way. But the other way is kind of say, okay, give me a break. Let me just make the adversary stronger, and then I don't need to deal with any of that. And this is what happens in the device-independent setting. So in the device-independent setting, you know, not only that Eve is choosing the state, but Eve is also the one that prepares the measurements, the devices for Alice and Bob. Okay, so you can imagine a situation where Alice and Bob, they go to the QKD store and they ask, they want to buy a QKD device, and the manufacturer of the device is Eve. Okay, so they don't trust the manufacturer of the device. They don't know exactly what's going on here. They don't know if it's the, you know, maybe Eve tells them, yes, it's the Z and the X basis, but they don't really trust her. Or maybe there is just some noise in the system that, you know, they don't really know what's going on. So we don't want to model any of the kind of behavior of this physical device. Okay, so I just kind of treat it as a black box. Okay, I don't know what's going on inside. I don't know if it's quantum. I don't know if it's you know, I really kind of don't care from a theoretical point of view. I just take this thing, and I still want to be able to somehow produce a key for Alice and Bob using this device. Okay, so that's you can see it's making the adversary much stronger in this situation. So that's why should we do this? That's relevant for several reasons. So first of all, if we take like paranoid cryptographers, or we really don't trust the manufacturer of the device, okay, or if you're getting, you know, if one government buys the QKD setup from a different government. I think most importantly, it's actually very relevant for realistic physicists, in the sense that, again, you know, I can say XZ, but maybe it's not an XZ, and there is a noise, and the bus just crosses the street, and there is now noise that moved the entire system, and you know, we don't really want to model everything that can go wrong in the system. We don't know exactly what is the noise model here. These devices can be fairly complicated. Okay, so we just want to say, okay, I don't want to kind of, in the security proof, I don't want to base anything on a specific noise model, on a specific implementation. I want you theorists to deal with it, to prove security without making the experimentalist kind of have to implement something which is very, very specific, and any deviation from the implementation will open this side channel. Okay, so for a realistic physicist who doesn't want to kind of make sure that he's producing a specific system, this is this device-independent framework is really relevant. Okay, and also another reason is just it's very interesting. So it allows us, you know, I will show you that we can actually produce a key, and that's surprising. And it gives us, we are going to use fundamental physics aspects, like we used the uncertainty relation. Now we're going to use something else. So it also, by considering these kind of extreme models, we also get to learn a lot about fundamental physics. Okay, so it looks crazy. How can we create a key this way? So there's one thing that we do know when we look at this picture, and also that we can enforce, and this is the partition to Alice and Bob. Okay, so, you know, Alice and Bob, they go to the store, they buy the device, but they buy two different devices. So there is Alice's device and there is Bob's device. Okay, and they can, you know, they can go now to different rooms and put them in different rooms. So we do have this partition. We know that there is Alice's system and Bob's system. Okay, and we want to use that. We can tell them to put them far away from each other, or just make sure that, you know, they're in different locations. And this is something that we can use, and this is similar to those of you who are familiar with the multi-prover setting in classical cryptography. Okay, so we can think of having two non-interactive, two non-communicating provers, for example. Then this is very similar to that. I have these two devices, and you can think of it as having these two different provers. Okay, so I have these boxes here, and I have one for Alice, one for Bob, and I want to make sure that they are separated, that they cannot communicate with one another when I'm executing the protocol. Now it's this black box, this brown box here, right? So I don't know what's going on inside. I don't know it's quantum. Alice and Bob, definitely they cannot perform any measurements. There is no concept of, you know, perform a Z measurement on this box. It's just a box. Okay, the only thing that we can do is interact classically with these devices. So you can think of it really as, let's say, as a computer, and Alice is going to press a key on the keyboard. So this will be a classical information. So it's a classical bit X, 0, 1. So she's going to press a key corresponding to 0 and 1, and then the device will do something and will output us an output, classical output again, that we call A. Okay, so this is something, again, that Alice will just see on the display of the computer, for example. So it's classical information again. Okay, and the same for Bob. Bob can also interact classically with his device. So he will press a key on the keyboard. We denote this by Y, and then we'll get an outcome B. Okay, so this is a classical interaction with these devices. Okay, we don't know what they're doing. We're just having this classical interaction with them. Alice and Bob themselves don't do anything quantum here. Okay, now there is this concept of non-local games, and a specific, very famous non-local game is what we call the CHSH game. Okay, and this is this game here. So Alice and Bob's inputs for both of them, okay, they are all bits, they are all just 0 and 1. And we define a winning condition. This is what defines the game, which is this A XOR B is equal to X times Y. Okay, so if you know, X or Y, one of them is 0, both of them are 0, then we want A and B to be identical to one another. Then we say that, you know, if these are the results that we get, we say that Alice and Bob win. And if they get different outcomes, then we say that Alice and Bob lose. Okay, so this is a game. Now, if we take a distribution over the inputs, okay, so Alice and Bob are choosing the inputs, and let's say that each of them is choosing with probability half 0, probability half 1, okay, so uniform distribution over the inputs. You can think of it, and you can see that if these devices are classical, if there is a classical classical strategy here, then the best that you can do is 75% winning probability. Okay, so what is a strategy, or how do I write a classical strategy? So any behavior of this device, I want to write it as a conditional probability distribution. This is this thing here. So it's just a behavior. It tells me what is given x and y, for any value of x and y, what is the probability that the device outputs A and B. And a classical strategy can always be written in this form, in this convex combination over this lambda. This lambda, you can think of it as shared randomness. Okay, so this is what these two classical devices can share. And then we have a probability each, like Alice's device, what it will do, it will, depending on the input and this shared randomness, the lambda, will output some value for A, and the same for Bob. Okay, so any classical strategy can be written in this form. And it actually, if you think about it, and if you take a strategy where the devices, they always output 0 and 0, so deterministic strategy, then this gives you the 75% winning probability, and you can think about it a little bit and see that there's, you can't do better classically. Okay, but it turns out that there is a quantum strategy where in this case, the devices, before they start playing the game, they share an EPR state. Okay, so they have this maximum entangled state. And then when they get X and Y, the device will make a measurement, okay, specific measurement depending on X on Alice's side, and a specific measurement depending on Y on Bob's side. And with this strategy, they can actually achieve around 85% winning probability. Okay, so what we see here is what we call a quantum advantage. So there exists a quantum strategy, there are quantum devices that can do better than any classical device. Okay. Now, this is maybe just to, to make sure it's clear compared to things related to quantum computation here, because we have these two different provers, the two different devices. This behavior, this 85% winning probability, it cannot be simulated classically. Okay, so this is something this is just really a game. Once you have these two separated devices, it doesn't matter what you do. You can't you can't simulate the behavior of this quantum strategy of having this maximum entangled state and making measurements in two different places. You cannot simulate it classically. Okay, so it's impossible. It doesn't matter how much time these classical devices they cannot reach more than the 75% winning probability. Okay, so maybe if you want to compare it to what like from NP, or what from other proof systems. Okay, so in a standard proof system, you have maybe a language, and you want to check if a specific instance belongs to the language or not. What we have here is very similar. So in a non-local game, what we want to check is not if something belongs to a language. We want to check if the device is quantum. Okay, so if we play this game, this non-local game with the device, and we see that we get more than the 75% winning probability, that we know that something quantum must be going on inside. Okay, so this is kind of a certificate that we have a quantum device. Okay, even though we only interacted classically with it. Okay, so that's very cool. And in fact, it's not just a kind of a way to check that the device is quantum, but it turns out that this is also a way to certify that there is entropy. So production of entropy in this A. So in our QKD protocol, if we base a QKD protocol on this concept, then as before, we wanted to know that there is entropy in this outcome of Alice in Alice's measurement outcome, right? So you can see this A now. Okay, the device is doing something, we don't know what. Alice pressed 0 or 1. The device is doing something. It produced some classical outcome, and we want to know that this classical outcome has some randomness, so we can later continue with the protocol and produce a key out of that. Okay, so it turns out that this non-local game, the CHSH game, it really does that. It doesn't only tell us that the device is quantum, but also that there is randomness. So I will show this to you soon. Okay, so as I said before, if I think of just to make it slightly look at it from in a slightly different way or more formal way. So if I have these devices, then the way to describe behavior of these two devices is by using a correlation, what we call a correlation. So this conditional probability distribution tells us what they're doing. And here you can see, because it's a conditional probability distribution, there is no assumption regarding which measurements I'm making, what is like X and Y, what do they correspond to inside of this device. nothing about the state that is being measured, the dimension of the system. I didn't say anything. I'm just looking at this correlation. Then I can start studying the correlation space. Okay, so there are certain correlations that are classical, that can be achieved using classical devices. And there are certain correlations that are quantum, that can be achieved by using quantum devices, by sharing entanglement and performing measurements. Okay, so any correlation like this, it's a point in this correlation space here. So when I draw it like this, any point here is a conditional probability distribution. And a non-local game also, the physics side, we call it Bell inequality. You can maybe think of it as this kind of line here that separates classical from quantum. Okay, so it allows us to get a certificate that something, if we're above this line, then it cannot we cannot be classical device. It must be quantum correlation. So maybe just to highlight, there are also things outside of this quantum set. There is non-signaling set and there is the signaling set, which is just all possible conditional probability distributions. So not all conditional probability distributions are quantum. They don't all correspond to some quantum state and measurements. And in fact, it's if I just give you this correlation, it's hard to say if this belongs even to this quantum set or it's somewhere outside. It's actually an undecidable problem, so it's really, really hard. Now, the classical deterministic strategy of just outputting 0, this is a point, you can see this is a point here on this corner of this classical set of strategies. And this optimal quantum strategy of measuring this EPR pair, you can see this as a point here, on this, like really in the edge of the quantum set. Okay. Now, so that's okay. You also have the references. So then there is a lot of work. But what we know today how to do is we know how to relate each point here to the amount of entropy which is being produced in this, when we're talking about the CHSH game, for example. This is the relevant plot. So there is an equation that describes this relation. So this is just a plot of a specific analytical bound. Okay, so what we see here on the x-axis, we see the winning probability in the CHSH game. So I said the 75% is this point here. Okay, it's the classical bound. And indeed, we know if it's a classical deterministic strategy, then device always output 0. Of course, Eve knows that the output of Alice's output is 0. There is no entropy. So this is this point here. On the other extreme, this approximately 85%. This is this optimal quantum strategy. In this case, we are measuring EPR states, and we know that we can produce 1 bit of entropy, so perfect randomness. So even doesn't know anything about this outcome of the bit. And we have this. So this is, it's very hard to prove it, but we have this bound that for any point here, as a function of the winning probability in CH game, we know how much entropy is being produced. Okay. So this basically, it's exactly the same take-home message that we had from the uncertainty relation. We just replaced now to some other fundamental aspects of physics. But again, you see that the winning probability in the CHSH game, okay, if you have your protocol, if in the protocol what you're going to do, I didn't write the protocol explicitly. So if the protocol, what you're going to do is you're going to play many times you have many copies of these devices, okay? And you play many times the CHSH game. You choose some subset of the rounds and check if you won or lost the game, and then Alice and Bob can calculate the average winning probability. Okay, so this average winning probability, and this is Alice and Bob's observed data. Okay, and this is some number here. Okay, so this some number here, what they observe in the protocol when they check the violation for the CHSH game. This tells them exactly how much entropy they have in Alice's output given Eve's quantum side information. Okay, so again, the quantum physics allows us to basically bound Eve's knowledge using what Alice and Bob observed during the execution of the protocol. Okay, so this is now just a different kind of law of physics that replaced what we had in the previous, in the Eckert 91 protocol. Questions? this? No? Do we have some questions, or it's all?
Okay. So yeah, we have a question. So in a quantum setup, we have a pre-shared EPR. What is the analogy for that in the classical cryptographic setting?
What is the analogy? So in the quantum case, we are kind of, you can think of sharing the CPR state, and I would say in the classical case, this will be shared randomness. Okay, shared classical randomness. So I don't know if this answers the question, but
yeah, I think it does.
Okay.
Yeah, we don't have.
So a classical device is basically like sharing the two devices. They can share some classical randomness, and then they can, they can decide what the output. But this optimal classical winning probability turns out to be when you don't even need this shared randomness. So this you can look at it yourself later. You can figure it out. Okay, and see this is correct. Okay, so you don't, for the optimal winning probability here, you don't even need this shared randomness. Okay, and for the quantum case, once you're starting, like here will be the maximally entangled state, and in the middle you can have other entangled states. It doesn't even matter. I don't need to know what the entangled state here. I just need to know how much, what is the winning probability in the CHSH game. Okay, and this gives me a bound on how much Eve knows about the output, Alice's output. Okay. Okay, so we have this relation. So again, what the protocol is, again, I'm like always thinking about this IID setting. So the protocol is just, I have these devices. I don't know what they are. Alice and Bob just play many times, one after the other, the CHSH game. They choose a subset and check what is the CHSH violation, look at the average violation. Okay, now we have basically the same security proof as before. So instead of having the uncertainty relation, now we have like this winning non-local game as a proof of quantumness and a proof of the production of entropy. So we have a lower bound on this von Neumann entropy in a single round as a function of the winning probability in the CHSH game. This is what the plot I just showed you. And then we can do exactly the same. So in this particular case, we can apply again the entropy accumulation. We need to show that we can use it. Then we have this quantity here. Sorry. It gives us a lower bound on the, sorry, I just need to drink. It gives us a lower bound on the entire amount of smooth mean entropy in the entire protocol. We apply a quantum proof extractor. Then we get the secrecy. And then we get the security. Okay, so the thing that I changed here is just really this fundamental aspects of physics that I'm using, and now just using a different law of physics in order to get this to start this chain here. Okay, so I'm saying okay, security. In the case of the Eckert 91 protocol, the BB84. I told you that this security definition with the secrecy correctness with this trace distance, I told you this is equivalent to the composable security definition, and this is what kind of justified using it. So here I just want to say it's not it's not actually composable. So when we're using this definition, it's almost composable. So in most cases, it's very hard to define it. So if you're not, if you're not reusing the same device, okay, this same brown box after the end of your protocol, if you kind of throw it to the garbage, then everything is composable. You can continue, you proved security and everything is fine. It's a composable security. But because we don't know what's going on with the devices, what happens in these brown boxes, if we're not throwing it to the garbage and we're going to use it in another protocol, then it gets tricky, okay? Then we don't have like this full composability, and this is something that comes up in a device-independent setting because of this kind of extreme situation. So we understand exactly what this security definition that we're using means, but it's not like fully composable in the sense that I used before. Okay. So just some disclaimers. So I mean, I made it look really easy. Like there is this sequence of steps, and I'm just, I'm changing the first step because I now have a different a different model and then everything flows. So this sequence of steps doesn't always work. So there are many QKD protocols with security we don't know how to prove, okay? And among them, there are also protocols that are of high relevance in practice. So protocols which are very efficient or very noise tolerant, but we actually don't know how to prove their security. So it's not like you have this clear picture all the time. I'd also say that we're also looking for new protocols all the time. And one thing which is really interesting and people are trying to look at, and maybe also people from classical cryptography can kind of join the effort, is to change the classical post-processing. So in the classical post-processing that I mentioned before, we had this error correction, the classical error correction, and the privacy simplification, which was applying an extractor. And this you can all do only like with communication, classical communication from Alice to Bob. So you don't need Bob also to send information. And there is a very interesting question whether there are like more complicated classical post-processing protocols, but they need to be secure in the presence of a quantum adversary. And we're looking for protocols of this form these days. So if you have some ideas for more interesting post-processing, classical post-processing steps, then that can be very, very relevant. And also I want to say that I kind of show you two different extreme settings. So we had this PB84, the Eckert 91, where we have this EX in the Z, we had qubits, everything was very clean. And on the other hand, I showed you this device independent, where I don't know anything about my device. I don't know the dimension, I don't know what's going on at all, I only have classical interactions. So these are kind of two extreme models, but there are many intermediate models, okay, that we need to learn to analyze. So there's a full field of like called semi-device independent protocols and other settings that are very interesting. And again, we don't know how to necessarily apply all these steps that I showed you to get all of these intermediate security proof for intermediate protocols. Okay, so I end with this. So I just few last words. So in QKD, as I showed you, everything goes quantum. Okay, so we have a composable security definition, which is something dedicated to take care of. We have these quantum entropies, many different types of entropies, and we have the quantum side information, the quantum states on which we evaluate these entropies. So this is also very delicate. We don't just take the classical thing. We have quantum proof extractors, which are, as I said, also delicate because not all classical extractors are also quantum proof, and we need to take this into account. And then on the other hand, I also showed you how we can actually exploit the laws of quantum physics to prove security. So this is kind of the take-home messages that I showed before, that the laws of quantum physics, basically, they allow us to bound Eve's knowledge from the data that Alice and Bob observed during the execution of the protocol without imposing any other assumptions on Eve. Okay, so only the laws of quantum physics, but they allow us to do exactly this. So Alice and Bob can interact, they can execute a protocol, and they can decide if Eve interferes too much, if she has too much knowledge or not. And the last thing I want to say is that I didn't talk about the key rates. I didn't show you specific implementations and how we play with all these epsilons. So there is n as a parameter, and there are epsilons, and there are different, many different errors that we can take into account. When if you open the security proofs, you will see it's very complicated. There are many parameters, and we want to kind of optimize everything at once, such that we get the highest key rate per security level, for example. Okay, so this is something that you can see in the paper. Here I focus just on the most basic theoretical aspects, but the bounds, they do matter, and they do matter because we're implementing these protocols. Okay, so it's very important, and these things they must be taken into account in the security proof. So someone asked before if the uncertainty relation is tight. So again, if my first step in this sequence of steps to prove security is not tight, then all of my final results will not be tight. And it's very important for us to get tight results, to get very high key rates, because it's being implemented. So these things are really we really care about them, and we really, every time kind of try to change and modify, use the best kind of law of quantum physics that allows us to bound the entropy in the tightest way, and also make sure that all the other steps are give us the tightest result that we can. Yes, and that's it. With this, I end. Thank you very much.
Thank you very much. So unfortunately, I think that we don't have more time for questions. So maybe, sorry?
Also, feel free to write. People can write questions in Slack, and I will reply later if they have something. That'd be great. Yeah. Thank you very much.
Perfect. Thank you very much.